Hey everybody, welcome to semester 2, day 2 of summer school geometry. Today we're going to be talking about two types of special right triangles. And as you can see up here, the two triangles in particular that we're talking about have these combinations of angles in them. And if you notice, they all add up to 180 just like any other triangle, but in specific, these are right triangles, so that means one of the angles has to be 90 degrees, one of them has to be a right angle. And then the other two add up with 90 to get 180, same thing over here. So these two particular triangles are interesting because they follow a certain set of patterns, and the rule works every time. And so as you can see here, I've sketched those two types of triangles. This is a 30, 60, 90, and then this is 45, 45, 90. What's special about the 30, 60, 90 triangle on the left here, this blue triangle, is if I reflect this triangle and I draw the same dimensioned triangle on the other side. So I'm going to sketch this real quick in just dotted lines so you can kind of see what the reflection would look like. So I reflected this triangle over the long side and I reflected it over. So if I reflect it over, that means that the angles have to be the same over here because I've just made a copy of the triangle and just reflected it over. So 60 degrees over here means 60 degrees over here. This 30 degrees also gets reflected over this way. So there's that. So now what you notice right here is I have this larger triangle. I still have the original 30, 60, 90, but since I doubled it and reflected it the other way, I look at this entire triangle, and this is what we call an equilateral triangle, the bigger triangle on the outside. I will highlight that so you can kind of see it. The larger triangle out here is equilateral because if you look at the three corners of the equilateral triangle, 60 degrees, 60 degrees, and these two combined make 60 degrees as well. So this is an entire equilateral triangle. And what you can say is that the three sides of an equilateral triangle are always going to be the same. So these three sides here are congruent to each other. They're the same length. So if this had a length of x, and I drew this entire side over here, this entire piece would also have the length x, which means that just this half distance right here would be 1/2 of that, 1/2 x. So now what I'm going to do is I'm going to erase all this stuff that I drew over here. Let me get rid of all that stuff and get back to my original triangle. So now we've stated that this side is x. I just gave it that arbitrary variable length, some number. This short leg that's connected to the right angle is half of this side right here. And this is now, if we think about this as a right triangle, this longest side here is the hypotenuse. This short leg is one of the legs, and this other leg is the other one. So whenever we think about right triangles in middle school, you probably remember the Pythagorean theorem. And so we can use the Pythagorean theorem to figure out all three side lengths if we know one of them. The same rules kind of apply here for a 45, 45, 90 triangle, except we're not going to draw the other triangle like I did over here. What I'm going to do over here is just identify what kind of a triangle this is. So what I'm going to do to rotate it like this. I know it looks kind of off now, but you still know that this is 45, this is 45, and this is 90. Now, earlier in semester 1, we learned about isosceles triangles. An isosceles triangle has two sides that are the same length, and the third side is a different length. So this is isosceles right here, which means that these two base angles are both 45 degrees. They have to be the same if it's an isosceles triangle. So now I can say that if this is some length x, then this one over here is the same length, and you can kind of figure out the third side using the Pythagorean theorem. So let's look at some examples on how we do that. So right here I have this triangle. It only has one angle marked as a number, 60 degrees right here. But I can use some context clues to figure out the other angles. Now this is a box, so it's 90 degrees. So a box, that means it's always 90 degrees. So this has got to be a 60, 90, and this last angle has to make these two combine up plus this one to make 180. So this is a 30, 60, 90 triangle. So now I can use the rules that we used earlier. What I'm going to do is I'm going to draw as best as I can here and sketch this other triangle reflected over the long side. So now I have this bigger triangle. And what we talked about up here, whenever I reflected the triangle, just like this, okay, we said that all the sides are the same length. So this guy over here has to be y. This guy over here has to be y. So now if all these three sides are the same, and I know half of this one right here, if I count the total side and I know half of it is 6, then the full side has to be multiply that by 2. So this y is going to be equal to 12. Y is 12. So now let me erase this stuff over here, get rid of all that. That was just to kind of show you how you set up the problem. So we got 12 is the hypotenuse now of the right triangle. So we've got 6, 12, and I need to figure out what this last length is. Now we can apply the Pythagorean theorem here. So before, whenever you learned Pythagorean theorem, we had a squared plus b squared equals c squared, but I don't see a, b, and c here. What we can do is, instead of putting a squared plus b squared, is put these two legs squared right here. This is a leg, this is one of them, and this is the other one. So those two things are a and b. It doesn't matter, you can put whichever one wherever you want, as long as one is a and one is b. Apply the rules of algebra, solve for x here, solve for the missing variable, so we can figure out what this last dimension is. And that's what we get for x right there. Okay, let's try a different example with the 45, 45, 90. Okay, so over here, we know that these two angles are 45 and 45. So that means that this last right angle is obviously 90 degrees. Now what we need to think about is, what are the two leg lengths? Since this is a 45, 45, 90, this is an isosceles triangle. These two legs are the same length. So that means that both of these have to be x. This is already labeled x, this is already labeled x. The hypotenuse is 6. I need to figure out what x is here. So let's use the Pythagorean theorem again, because this is a right triangle. Right triangle, you can always use Pythagorean theorem. So just like before, we had a squared plus b squared equals c squared. But now a and b are like these two guys. So they're both x. So a squared plus b squared, x squared plus x squared equals the hypotenuse, which is 6, and then we square it. So now we just apply the rules of algebra and we solve this equation. So right here, I see two of these x squareds. If we're combining like terms, we need to add those two together, but the exponents stay the same. So this is two of them, 2x squareds is going to be equal to, and 6 squared is 6 times 6, or 36. Okay, now let's talk about how you simplify a square root, how you make this as simple as possible. When we have the square root of 18, we want to check, are there any other numbers that we can simplify 18 into? Meaning, are there any square numbers? The square numbers are the numbers you can take a perfect square root of. So like 9. If you take the square root of 9, you get an even number of 3. But if you take the square root of 18, we end up getting a decimal. So for example here, if I did the square root of 18, notice how I get this long decimal, 4.24. That means 18 is not a perfect square. But I could take the square root of some other numbers, like if I did the square root of 4, I get whole number 2. Or if I do the square root of 16, I get 4, another whole number. If I did 25, that's equal to 5. I can keep going. Now what I want to do here in this example is find another number that's a square number that goes into 18, and that number is 9. If I did square root of 9 times 2, because 9 times 2 is 18, I can simplify this guy right here. Now what I do is I break apart the square root and I put that this is equal to the square root of 9 times the square root of 2. We can simplify square roots like that. So we put each of these into their own house, into their own square root, 9 times 2. And now I simplified this first one right here. The other one can stay the way it is. And here I get 3 square root of 2. So on Delta Math, it might ask you to simplify the square root on some of the problems. And in that case, you would just follow this process and try to get it down to a simpler square root that has possibly a whole number in front of it. Okay. Let's look at another example here, 2 more examples. So here we've got the hypotenuse is 13. We've got x and we've got y as our 2 legs. But we don't know either of the 2 legs yet. We can figure one of them out though. We don't need the Pythagorean theorem just yet. Let's first sketch that other side, that other reflection of the triangle. The reason I'm doing this is because this allows me to figure out one of my legs. It allows me to figure out x. We talked about the equilateral triangle when we reflect this over. 60, 60, and 30 plus 30 is 60. So that means 13 has to be all of these outer edges. And that means x is half of the outer edge, so x is half of 13. So now, half of 13 is 6.5. So x is going to be 6.5 because it's half of 13. That rule will always work for a 30, 60, 90 triangle. This is 30 degrees. Okay, so the shortest side is always half of the hypotenuse for a 30, 60, 90. So in the future, once you get a little bit better at these, you don't have to keep on drawing the triangle. You can just say, this short leg is half of the hypotenuse. And then all we need to do is now just Pythagorean theorem to figure out the last leg. So 6.5 squared plus y squared is equal to 13 squared. A squared plus b squared equals c squared, same thing here. So I'm not going to go through and finish this problem. I've already worked a couple of examples on that. So you can try this on your own and simplify. It's just like solving for x, you simplify and solve for y here instead. Okay, and then the last example here. Let's talk about this 45, 45, 90. It's an isosceles, so that means that these 2 lengths are equal to each other. It's going to be a squared, so I'm using this as a. B squared is this other leg, which is the same thing again. So plus the same thing again squared, plus 2 square root 2 squared equals x squared. So now let's think about how we can simplify this. I'll do one of these so that you can kind of see how you would square it if you're not sure. Whenever we do these, we're multiplying whatever's in the parentheses times itself. Just off to the side, I'll write it down over here. 2 square root of 2, 2 square root of 2. So I got both of these guys here. 2 times 2 is equal to 4. And root 2 times root 2 is equal to just a 2. So this ends up being 4 times 2, which is 8. So this is actually 8 plus 8 equals x squared. And then you can go continue the equation and solve for x in that case. And it's pretty quick. 16 equals x squared. So that means 4 is equal to x. Go ahead and look at your Delta Math assignment for today. And please email me if you have any questions. My email address is right here, or you can just message me on Canvas.